On July 1st, 2025, a telescope in Chile caught something that should not have been there. Moving too fast, pulled in from deep space, NASA confirmed what it was. The third visitor in history from another star, a frozen giant older than Earth, leaking strange metals, emitting gases we cannot explain. It came closer than most people realize. Before we're done, you'll see why every major telescope is still locked on it. If this grips you, tap subscribe. Stay close, the story is still moving. At 4:28 in the morning, Mountain Time, a robotic telescope high in the Chilean Andes captured a smear of light that did not belong to our sky. It was July 1st, 2025. The telescope is part of a system called ATLAS, short for Asteroid Terrestrial Impact Last Alert System, a network funded by NASA to watch for rocks that might hit our planet. That night, the software flagged something unusual, a faint dot moving too fast against the background stars. The astronomer on duty pulled up the data. The object was crossing the sky at a speed that made no sense for anything born in our solar system. Rocks that belong here move along predictable curves, tugged by our star's gravity into loops that take years, centuries, or millennia to complete. This one was not looping. It was slicing straight through, like a bullet passing through a room. Within hours, the alert went out to the Minor Planet Center, the clearinghouse that tracks every new object in the sky. Other telescopes across the world swung toward the same patch of stars. Observatories in Hawaii, Arizona, South Africa, and the Canary Islands all confirmed it. The object was real, the speed was real, and the speed was the problem. At the moment of discovery, it was moving at 137,000 miles per hour. For comparison, the fastest spacecraft humans have ever launched tops out at roughly that speed only after years of gravitational slingshots. This object was already doing it, and it was doing it while still far out, beyond the orbit of Jupiter, where our star's pull is weak. Nothing born inside our solar system reaches that velocity on its own. That single detail told astronomers something extraordinary before anyone had even measured its size. This rock was not from here. It had been travelling through empty space for an unknown amount of time, launched long ago from somewhere else, and it had finally crossed paths with us. The scientific term is interstellar. In plain words, it means the object came from another star. Only 2 others had ever been confirmed. The first was spotted in 2017, a cigar-shaped sliver called Oumuamua that passed through and vanished before we could study it. The second, in 2019, was a clear comet called 2I/Borisov. 2 visitors in 8 years, and now a third. NASA made the official call within 72 hours. The object was designated 3I/Atlas. The letter I stands for interstellar. The number 3 marks it as the third we have ever seen. The name Atlas honours the telescope that caught it. What happened next surprised even the scientists who expected surprises. As more telescopes pointed at the object, the measurements kept getting stranger. The size estimates climbed. The composition readings refused to match anything in our catalogues. And the trajectory, when plotted on a map of the solar system, showed it heading inward, deeper, on a path that would bring it closer to our Sun than Mars, and then closer to Earth than most people ever heard about in the news. In the first 48 hours, we only knew one thing for certain. Something enormous had entered our neighbourhood, something that had been travelling longer than anyone could yet imagine, and the next reading would reveal just how far it had come. Speed is the fingerprint of an interstellar object. everything else can lie. A rock can look ordinary, a tail can form late, a colour can mimic local comets. But velocity, measured against the gravitational pull of our star, tells the truth every time, and the velocity of 3I/Atlas shouted, "Our star holds everything around it on an invisible leash. The leash weakens with distance, but the rule is strict. Anything falling toward the sun from far away picks up a specific, predictable speed by the time it reaches the inner solar system. Comets from the icy edge of our system, the place called the Oort cloud, typically arrive at around 26 miles per second. That is already blistering. That is the natural ceiling for something born here. 3I/Atlas blew past that ceiling. When first detected, it was moving at 36 miles per second relative to the Sun. By the time our star's gravity pulled it in, at its closest approach, it hit 42 miles per second, which works out to about 153,000 miles per hour. At that pace, it could cross the distance from New York to Los Angeles in under 60 seconds. The excess speed was the smoking gun. Astronomers call the leftover energy hyperbolic excess velocity. A number above zero means the object is not bound to our star. It came in fast, it will leave fast, and our sun cannot hold it. Think of a ball tossed through a garden fountain. The fountain tugs it sideways, the ball arcs, but it keeps going. That is what our solar system looked like from the object's point of view. A brief curve in a very long journey. The calculation was brutal in its clarity. Once the object leaves our neighbourhood, it will return to roughly the same 36 miles per second it arrived with. Our star took nothing from it and gave nothing back. It simply passed through. That detail carries a heavier meaning once you sit with it. The object was already moving at that velocity before it met us, which means something else, somewhere else, launched it at that speed long ago. A gravitational slingshot past another star. An ejection from a young planetary system still shaking loose its debris. A close encounter with a binary pair that flung it into the dark. We do not know the exact mechanism, but the math of deep space is unforgiving, and 36 miles per second is fast even by galactic standards. Here is the part that sharpens the chill. A rock moving at that speed does not cover short distances, it covers cosmic ones. In a single year, it crosses more than 1 billion miles. Over millions of years, it crosses light years. Over billions, it crosses the spiral arms of entire galaxies. And astronomers already had reason to believe this one had been travelling a very long time. The direction it came from offered a clue, not a random patch of sky. A specific region, weighted toward the old, slow stars that ring the centre of our galaxy in a halo of ancient light. The speed said it was not from here. The direction said it was not from recent history either. It was from somewhere deeper, somewhere much older than our sun. Size changes everything. A small interstellar object is a curiosity. A large one is a problem for the models. When the first rough measurements of 3I/Atlas came back, the numbers did not just raise eyebrows, they broke a ceiling. The Hubble Space Telescope turned its optics on the object in late August 2025. Working through the glare of the comet's glowing coma, astronomers peeled away the haze to estimate the size of the solid core underneath. The nucleus, the rocky icy heart of the object, came in somewhere between 1,400 feet and 3.5 miles across. On the upper end, that is larger than Mount Everest is tall, tumbling through space at 100,000 miles per hour. Compare that to its two predecessors. Oumuamua, the first interstellar object ever spotted, was only about the length of a football stadium, 2I/Borisov, the second, was less than a mile wide. 3I/Atlas is in a different weight class entirely. Some estimates of its total mass reach 33 billion tons, which is more than every human-built structure on Earth combined. That scale creates a mystery on its own. Scientists who model how interstellar objects are ejected from young star systems ran the numbers. For an object this massive to exist, travelling alone between stars, the supply line has to be enormous. A single star system does not casually fling out 3-mile rocks. It flings out thousands of small chunks and very rarely a big one. So if we have spotted 3 interstellar objects in less than a decade and one of them is this large, the math suggests something uncomfortable. Either we got extraordinarily lucky to catch the largest outlier on our very first try, or interstellar objects this size are far more common than our models allow. Both options rewrite part of our understanding of how planetary systems form and die. There is also the question of what a rock this big even does. Most comets in our solar system are smaller. A 3-mile nucleus is closer to the size of a small moon. It carries its own gravity, its own thermal behaviour, its own complicated internal structure of frozen gases, dust, and older ice. It would not simply heat up and dissolve near a star. It would burn in layers, slowly, releasing different gases at different depths over months. And that is exactly what astronomers started to see happening. As 3I/Atlas fell deeper into the solar system, its surface warmed. Ice sublimed directly to gas. Dust lifted off. The coma grew. By late summer, measurements showed the glowing cloud around the nucleus stretching more than 16,000 miles across, wider than 2 Earths placed side by side. The tail began to form, stretched into a faint streak by the pressure of sunlight and solar wind. To most observers, it looked like a comet doing what comets do. To the teams running the numbers, it looked like something much stranger. Because the standard model of comet activity predicts a smooth, gradual awakening as the object approaches the Sun. 3I/Atlas was not following that curve. The first signs of activity had been detected months before the object was even officially discovered, at a distance where no ordinary comet should yet be active. Something was heating it from the inside. A curve in space tells a story. Trace the path of a comet, and you are reading a biography written in gravity. The shape of 3I/Atlas's orbit, once astronomers had enough observations to plot it precisely, revealed a biography unlike anything humans had mapped before. Most objects in our solar system travel on closed loops. Their orbits are ellipses, stretched circles that pull them toward our star and then swing them back out, over and over again. A comet like Halley's takes 76 years to complete its loop. A distant ice ball from the outer reaches may take 10,000, but they all come back. The Sun holds them. 3I/Atlas did not have an ellipse. It had a hyperbola. The difference matters. An ellipse closes. A hyperbola does not. A hyperbolic path enters the neighbourhood of a star, bends around it, and then flies back out into open space forever. It is the signature of an object that was never captured and never will be. Think of a train passing through a station without stopping. It slows a little near the platform because of the crowd and the noise, then accelerates back to full speed on the other side. The measurement that decides it is called eccentricity. A perfect circle has an eccentricity of 0. An Earth-like orbit sits near 0.01. A long comet path might reach 0.9. Anything above 1 is unbound. 3I/Atlas came in with an eccentricity above 6. That number is not just high, It is among the highest ever recorded for any object observed in our solar system. It means the object was moving far faster than the Sun could ever hope to slow. The gravitational curve was barely a bend in a very long line. Once astronomers locked in the orbit, they could run it backwards in time and forwards in time. Backwards, the path traced toward a specific region of the galaxy. Forwards, it drew a clean exit out of our neighbourhood, past Jupiter, past the outer planets, into the dark between the stars. Perihelion, the closest approach to our star, would happen on October 29th, 2025, at a distance between the orbits of Earth and Mars. After that, the object would accelerate back outward, past Jupiter in March 2026, and vanish from view. It will never return. Sit with that for a moment. Everything else in our sky has a pattern. The planet's cycle, the asteroid cycle, even the most distant comets, dragged from the edge of our system, eventually come back. 3I/Atlas is a one-time event. Whatever it carries, whatever chemistry is locked inside its ice, whatever record of its home system it preserves, we have one window to study it. After that window closes, it is gone forever. That realization changed how scientists treated the object. A race began. Hubble, Webb, SPHEREX. Every major telescope on Earth and in space. Spacecraft already in deep space, on missions to Jupiter, to Mars, to the asteroid belt, were quietly reprogrammed to glance sideways as the visitor passed. The clock was not negotiable. Once 3I/Atlas left, the chance was over, and the measurements they grabbed during that narrow window would produce a reading that kept asking a harder question. Where exactly had it come from? Every object in space moves from somewhere, toward somewhere. For a rock passing through the solar system once and never returning, the direction it came from is a kind of return address. Astronomers call it the radiant. For 3I/Atlas, the radiant pointed into a region of the sky dense with stars, and more importantly dense with old stars. The object entered our neighbourhood from the direction of the constellation Sagittarius. That patch of sky is not random. It looks toward the centre of our galaxy, through a structure astronomers call the thick disk. Picture the Milky Way edge-on. You would see a bright, flat plate of stars spinning like a frisbee. That plate has two layers. The thin disk is where our Sun lives, full of younger, metal-rich stars born in the last few billion years. Below and above, there is a thicker, dimmer layer, the thick disk. It holds the old veterans of the galaxy, stars that formed early, before the Milky Way had finished assembling itself. Stars in the thick disk move differently than stars in the thin disk. They orbit the galactic center on tilted, elongated paths at higher speeds relative to the average. Any rock ejected from one of those old systems inherits that motion. A fast interstellar object arriving from that direction carries a specific velocity signature, and 3I/Atlas matched it. That single alignment carried an enormous implication. The object was not launched from a neighbouring star in our own cosmic backyard. It had come from deeper in galactic time, from a region populated by stars that were already old when our Sun was still a cloud of gas. Researchers who modelled the trajectory ran the estimate. Based on its velocity vector and its likely origin zone, the object's age could fall anywhere between 7 and 14 billion years. The upper end of that range is older than the universe's current estimated age of roughly 13.8 billion years, which points to uncertainty in the measurement rather than a paradox. But the lower end is already older than Earth, older than our star, older than every planet in our solar system. In plainer terms, this rock was already drifting through space when our sun had not yet ignited. That changes how you see the object. It is not a neighbour passing through. It is a traveller from a chapter of galactic history that no longer exists. The star system it was born from may have burned out long ago. Its parent star, if it was a short-lived giant, would have exploded and faded before multicellular life appeared on Earth. The object is, in a real sense, a messenger from the dead, and the messenger carries a physical record. Whatever ices locked into its surface billions of years ago preserved the chemistry of that ancient system. Every molecule held in its frozen shell is a sample of a place and a time we cannot otherwise reach. That is why telescopes across the world stopped what they were doing to study it. Not just to confirm an interstellar visitor, to crack open a time capsule. The first reading they pulled out of that capsule did not match anything on our shelf. If the age estimate holds, 3I/Atlas is older than the ground you're standing on, older than the oxygen in your lungs, older than every atom that ever organised itself into a living cell. An object this ancient forces a different kind of thinking. The number most researchers cite is 7 billion years at minimum. For context, our solar system is 4.5 billion years old. That means 3I/Atlas was already wandering interstellar space for roughly 2.5 billion years before our sun even lit up. When the cloud of gas that would become our star first began to collapse under its own gravity, this rock was already old, already drifting, already far from whatever system had made it. And it has been moving ever since. A rock cruising at 36 miles per second, given 7 billion years of runway, can cover a staggering amount of distance. Translated into cosmic terms, that is roughly 8,000 light-years of travel. It could have crossed the width of our entire galactic neighbourhood, looped past multiple star-forming regions, and passed through the gravitational wake of stars that have since burned out entirely. Consider the silence of that journey. 7 billion years of empty space. No atmosphere, no water, no heat except the faint dusting of light from distant suns. The object would have been cold beyond anything we can comfortably picture, its surface temperature hovering just a few degrees above absolute zero for the vast majority of its life. Its volatile ices, the frozen gases that would eventually form its coma, were locked up solid for all that time. Then, very recently on a cosmic scale, our sun's gravity caught it, pulled it in, and warmed it for the first time in almost the age of the Earth. That is the moment astronomers were watching. The first thaw in 7 billion years. The chemistry released in that thaw became one of the most carefully studied signals in modern astronomy. Every gas that came off the surface, every molecule in the expanding coma, was a sample that had been sealed away since a different era of the galaxy. Measuring it meant peering directly into the pre-solar chemistry of a distant, long-gone system. And the readings came back strange. The James Webb Space Telescope, using its infrared spectrograph, measured the gases escaping from the nucleus. Carbon dioxide dominated. In most comets native to our solar system, water vapour is the main outgassing product as the ice warms. In 3I/Atlas, the ratio of carbon dioxide to water was among the highest ever measured in any comet. It was, in the words of the lead investigator on the observations, at the extreme edge of the known range. That detail carried weight. Different mixes of carbon dioxide and water form at different temperatures, in different parts of a young planetary system. The chemistry of an object encodes its birth conditions. A carbon dioxide heavy signature suggests the object formed in a colder, more distant region of its home system, or formed around a different kind of star than ours. The reading was a first glimpse at alien geochemistry, a snapshot of a world we will never see, and the snapshot kept getting stranger. An object that old has a survival problem. Space is not truly empty. It is thin, yes, but over billions of years even thin things erode. Dust grains, stray hydrogen atoms, cosmic rays, the occasional kick from a passing star's gravity. A rock wandering between stars for 7 billion years should be beaten, cracked, stripped, and worn smooth. The fact that 3I/Atlas arrived still active, still outgassing, still holding volatile ices close to its surface is a mystery in itself. Start with cosmic rays. High-energy particles streaming through the galaxy at nearly the speed of light slam into anything in their path. Over a few million years, they can chemically alter the top layer of an icy body, breaking molecules apart and reforming them into heavier compounds. Given billions of years, that process creates a crust, a dark, hardened shell of processed material, sometimes called an irradiation mantle, that seals in whatever remains beneath. 3I/Atlas does appear to carry such a crust. Its surface is reddish, a colour associated in other comets with long exposure to radiation. The pigment is not from a coating of rust. It comes from organic compounds, complex carbon-based molecules built up slowly by the chemistry of radiation on ice. That reddish hue is essentially a suntan earned over geological time, but the coma is active. The ices below the crust are still there, still volatile, still ready to sublime once warmed by a nearby star. That means the crust, thick enough to protect the object for billions of years, is thin enough to crack open when pulled into a stellar system. Somewhere in its structure is a careful balance between sealing in and releasing. Now add collisions. Space between stars holds tiny grains of dust, each one microscopic but numerous. Over 7 billion years of travel, a 3-mile rock will intercept trillions of these grains. Each impact chips at the surface. Each hit releases a puff of heat. Simulations suggest that a lone interstellar object the size of 3I/Atlas should accumulate noticeable pitting, even outright damage, over that timescale. What astronomers see is an object that looks, from a distance, remarkably intact. Its rotation, measured by brightness variations as it tumbles, is steady. Its coma development is smooth. There are no obvious scars of catastrophic impacts. If it has been travelling for 7 billion years, it has either been extraordinarily lucky, or the interstellar medium is gentler on large objects than models predict. There is also the question of gravitational encounters. Over billions of years, a wanderer between stars does not travel in a straight line. It gets nudged. Passing stars bend its path. Giant molecular clouds tug it sideways. The spiral arms of the galaxy sweep it along. Any one of these encounters could have stripped it apart or flung it out of the galaxy entirely. That it arrived at our sun, intact and chemically active, means the dice rolled in its favour many times. The object, in other words, is a survivor. It came through a gauntlet that most interstellar rocks probably fail. What we see in our skies now is not the average wanderer. It is an outlier, the ones that made it. And as telescopes kept watching, the survivor started showing behaviour that did not match the known rules for comets at all. Go back to May 7th, 2025, 2 months before anyone noticed 3I/Atlas. The object was out past the orbit of Jupiter, more than 6 times farther from our star than Earth is. At that distance, the sunlight falling on it was dim and cold, less than 3% of what we receive here. No ordinary comet wakes up that far out, but NASA's Transiting Exoplanet Survey satellite a space telescope designed to find planets around other stars, had been collecting images of that patch of sky for weeks. When researchers went back through the archived data after the July 1st discovery, they found something quietly alarming. 3I/Atlas was already active in the May images, a faint, diffuse glow around the nucleus, the early signature of a coma months before it should have been possible. In our solar system, comets have a standard wake-up curve. Water ice, the most common volatile on a comet's surface, only begins to sublime aggressively when the object crosses about 3 times Earth's distance from the Sun. Closer in, the heat takes over and the comet blossoms. Farther out, the surface is too cold and the ice stays locked. That is the textbook pattern, built from decades of observations of local comets. 3I/Atlas broke the pattern. Activity was visible at more than double the expected distance. That meant something on the object was vaporizing at a temperature where water cannot. The obvious suspect was carbon dioxide, which sublimes at much colder temperatures than water ice. The Webb telescope measurements later confirmed that carbon dioxide was the dominant gas coming off the nucleus. A carbon dioxide-driven comet behaves differently than a water-driven one. It can wake up earlier, stay active longer, and release its gases in patterns that look unusual compared to local comets. That shifted the picture. 3I/Atlas was not just a comet from elsewhere. It was a comet made of a different mix, one that responded to warmth on a different schedule. The early awakening was the first concrete sign that the chemistry inside the object was not a copy of the chemistry we know. The discovery also had a practical consequence. It meant the observation window was longer than anyone had first assumed. Astronomers had caught the object not at the beginning of its activity, but well into it. That gave them more material to study, more gas to analyze, more coma to map. It also meant there was more to the object's structure than a simple surface layer. Different depths, different ices, different release rates. Think of the object like a layered dessert set too close to a heat lamp. The outer layer melts first, then the next, then the next. Each layer releases a different flavor into the air. A comet that wakes up early is a comet that is going to keep revealing new layers all the way through its pass, and each revelation is a new reading for the instruments waiting to catch it. And the second reading, when it came, was not about awakening or outgassing at all. It was about color. Color in astronomy is not decoration, it is data. A wavelength of light reflected off a surface, filtered through the chemistry of whatever produced it, carries a fingerprint back to the telescope. The colour of 3I/Atlas, once the measurements came in, told a story that was both familiar and unsettling. The object is red, slightly, enough to stand out in the filtered images. Not a fire engine red, not a visible dramatic shade to the naked eye. A reddish tint, measurable by spectrographs, in the same range of colour that astronomers see on a specific family of objects in our own solar system. The class is called D-type asteroids. They are dark, reddish bodies found mostly in the outer asteroid belt and among the Trojans, the swarms of rocks that share Jupiter's orbit. D-type asteroids are interesting because of what they contain. Their red colour comes from tholins, which are complex organic molecules built from simpler carbon compounds over long exposure to radiation and ultraviolet light. Tholins are the same class of compounds that give parts of Pluto, parts of Titan, and parts of distant Kuiper Belt objects their reddish hues. They are what happens when carbon-based ices sit out in cold, irradiated space for hundreds of millions of years. So a reddish tint on 3I/Atlas is a signature. It tells astronomers that the surface of this rock has been exposed to radiation for a very long time. The colour is consistent with the age estimate. It is consistent with billions of years between stars. It is consistent with a hard, processed crust built up by cosmic rays over a timescale longer than our solar system has existed. It also connects 3 I/Atlas to something closer to home. The previous interstellar comet 2I/Borisov was redder than most solar system comets and also resembled certain distant bodies in our own system. In other words, both interstellar comets we have studied in detail have shown surface chemistry that looks, at a glance, like objects formed far from their parent stars. That similarity is not a coincidence. It points to a universal rule. Objects ejected from young star systems tend to come from the cold outer regions, where ices are plentiful and the gravitational grip of the host star is weakest. A gentle shove, a passing gas giant, a slight gravitational perturbation, and the object flies free. The inner, rockier bodies stay put. Only the outer wanderers get launched. So when we see 3I/Atlas, we are likely seeing a cousin of our own distant icy bodies, a Pluto analogue, a Kuiper Belt refugee, something that formed at the frozen edge of another star's nursery, then spent the next several billion years adrift. The colour also hinted at what was hiding under the surface. Beneath the reddish crust of processed tholins, the fresh, unweathered ices of the object's interior would be a different colour entirely. Likely much lighter, likely less processed, likely loaded with the original volatile compounds that formed during the object's birth. As the crust cracked and the coma grew, those inner materials would finally see sunlight for the first time in billions of years, and when they did, they would expose a chemistry that nobody on Earth had expected. As 3I/Atlas fell deeper into the solar system, it grew, not the nucleus, which stayed roughly the same size, but the glowing halo surrounding it, the coma. A coma is not part of the comet itself. It is an atmosphere of released gas and dust, wrapped around the nucleus as ices sublimate. The sun's warmth drives the release. The solar wind pushes it outward. What begins as a small fuzz around the solid core can balloon into a cloud larger than a planet. By late August 2025, the coma of 3I/Atlas spanned roughly 16,000 by 15,000 miles. Wider than Earth, end to end, and nearly wide enough to swallow 2 Earths placed side by side. All of it glowing faintly in telescope images, lit by reflected sunlight and the ultraviolet excitation of the gas molecules inside. Think about what that means physically. The solid nucleus, maybe 3 miles across, was the seed at the centre. Around it, gases and dust escaping from the surface formed a slow, expanding shell. Those gases did not stop at the edge of the visible coma. They kept flowing outward, streaming away from the nucleus at thousands of miles per hour, eventually joining the solar wind and being carried off into space. Every second, the object was shedding mass. Measurements from NASA's Swift Observatory, looking at the ultraviolet glow of hydroxyl gas, a molecule formed when sunlight breaks water apart, gave a specific estimate. At a certain point in its inbound journey, 3I/Atlas was losing water at roughly 40 kilograms per second. That is the mass of a small adult, every second steadily bleeding off into space, and water was not even the main thing leaving. The carbon dioxide release was higher. Other gases joined the mix, methane traces, cyanide, organic compounds that flared under ultraviolet light and showed up in the spectrographs. The coma was not uniform. It had structure, jets, bright spots where particular vents on the nucleus were pumping out material faster than the surrounding surface. These jets, visible in high-resolution images, rotated with the nucleus as it spun. Each rotation pointed the jets in different directions, sweeping the ejected material into spiral patterns, like a sprinkler tumbling through the air. That level of detail matters because it tells us about the internal structure of the object. A smooth, uniform comet would outgas evenly. A jetting comet has weak spots, cracks, buried pockets of more volatile ice that erupt when they warm. 3I/Atlas had jets. The object was not a uniform ball of ice. It had texture. It had geology. It had a surface that was cracking in specific places as it heated. The tail came next. Solar wind and radiation pressure pushed the released gases into a long, faint streamer stretching away from the sun. By October, the tail was visible in long-exposure images, a dim smear behind the nucleus, pointing away from the sun's direction in classic comet fashion. In ultraviolet, the tail was brighter. Hubble and ground-based telescopes captured a diffuse cloud of hydroxyl and water vapor, extending far into space behind the object. The Coma and tail together acted as a laboratory. Every instrument pointed at them was reading the chemistry of a world that had formed around another star. And one of those readings, pulled out of the UV spectrum, were about to become the single strangest signal yet. It involved a metal that, in the quantities observed, had no business being there at all. The Webb telescope did not make many people nervous when it pointed at 3I/Atlas. It was designed to stare at exoplanets, at the early universe, at the faintest infrared glimmers from billions of light years away. A bright, close, outgassing comet was, on paper, an easy target. The instrument had the sensitivity to pick apart the Coma molecule by molecule. The measurement that came back unsettled the comet community. In a typical comet from our solar system, water vapor dominates the outgassing. Water is the most common volatile ice, and as a comet approaches the sun, the water signal rises above everything else. Carbon dioxide is usually present, but in a subordinate role, maybe 1 part carbon dioxide to every 20 or 30 parts of water. Webb measured the ratio on 3I/Atlas. The carbon dioxide was not a side note, it was competing with water directly. In some measurements, the carbon dioxide emission was higher. The ratio was, according to the lead investigator, among the highest ever observed in any comet, local or interstellar. That fact reshuffled the object's biography. Carbon dioxide freezes at much lower temperatures than water. In a forming planetary system, a body that locks in a lot of carbon dioxide ice is usually forming in the colder outer regions, far from the star. There is a specific zone in every young system, a distance from the central star where certain ices can freeze and others cannot. Astronomers call these zones snowlines. There is a water snowline, a carbon dioxide snowline, a carbon monoxide snowline. Each one marks a boundary. A comet born with carbon dioxide dominance suggests it formed past the carbon dioxide snowline, very far out. In a very cold part of its home system, possibly around a dim or low-mass star, where even the carbon dioxide snowline was close to the parent body. Alternatively, the object may have been through chemical processing over its long interstellar journey. Water ice near the surface could have sublimated away during close passes to other stars, leaving behind a relatively higher proportion of the lower volatility carbon dioxide. That is the slower, more patient explanation, and it is also consistent with the data. Either way, the carbon dioxide signal was telling us something the object could not say in any other language. Its birth environment, or its long aging process, was not like the comets of our own neighbourhood. It was a piece of foreign chemistry. There was more. The ratio of carbon dioxide to water is not the only diagnostic. The absolute production rate matters. The daily variation matters. The pattern of how the ratio changed as the object got closer to the Sun matters. All of those signals were being tracked, and they all pointed in the same direction. 3I/Atlas was a comet built on a different recipe. A recipe probably set in the cold outer reaches of a distant planetary system billions of years ago, then preserved almost perfectly in the deep freeze of interstellar space. That made the next reading even harder to explain. Because while carbon dioxide could be explained by a cold birth, the next anomaly involved an element that should not have been in the gas cloud at all, a metal. In July 2025, only weeks after 3I/Atlas was discovered, the Very Large Telescope in Chile caught an emission line that stopped a team of astronomers cold, a sharp signal in the ultraviolet spectrum at a wavelength that has one known source in cometary gas: nickel. Metal vapor is not the first thing you expect to see streaming off a comet. Nickel and iron are refractory elements. That means they only vaporize at very high temperatures, typically above 1000 degrees Fahrenheit. A comet drifting a few 100 million miles from a star is nowhere near that hot. The surface of 3I/Atlas, even near perihelion, was still cold enough to be covered in ice. The physics said no metal should be coming off it, and yet the signal was there. Clear. Repeated. Confirmed by multiple observatories. The mechanism, researchers decided, had to be indirect. Somewhere on the nucleus, a class of compounds called metal carbonyls could explain the result. Nickel tetracarbonyl, specifically, is a molecule that pairs nickel with carbon monoxide and, unlike pure nickel metal, breaks apart at cometary temperatures. When it breaks, it releases free nickel atoms into the coma. The emission line we see is those free atoms glowing under sunlight. So far, unusual, but not impossible. Nickel had also been detected in the coma of 2I/Borisov. It had been detected in some solar system comets, even ones far from the Sun. The existence of the signal was not the mystery. The mystery was what was missing. Because when the spectrograph scanned for the companion signal, the one that always appears alongside nickel in local comets, they found almost nothing. Iron was nearly absent. In every comet previously studied in our solar system, nickel and iron appear together in roughly equal proportions. That makes physical sense. The two metals are formed in the same stellar furnaces, scattered through space together by supernovae, incorporated into planetary systems side by side. When a comet outgasses refractory metals, nickel and iron show up as partners. 3I/Atlas was producing nickel without iron. The ratio was, in the words of the observing team, extreme, unprecedented. An outlier compared to every solar system comet in the database, and even compared to 2I/Borisov, which had roughly normal proportions. The nickel to iron ratio on 3I/Atlas was at the far edge of anything anyone had ever measured in space. The initial explanation pointed to temperature. Nickel carbonyl releases nickel at lower temperatures than any iron-bearing compound. If the surface of 3I/Atlas was warm enough to liberate nickel carbonyl, but not warm enough to liberate the corresponding iron carbonyl, you would see exactly what the spectrographs were seeing: a selective release. Nickel-rich outgassing without iron. That is a reasonable explanation. It even predicts what should happen next. As the object gets closer to the Sun and heats up more, iron should start appearing in the spectrum. As distance shrinks, the nickel to iron ratio should climb back toward the normal range. And the data did show that shift partially as 3I/Atlas approached perihelion. Iron began to appear, but by then the original anomaly had done its work. the conversation about what nickel without iron means, chemically and otherwise, was already spreading. And one researcher at Harvard had started saying something out loud that most of his colleagues would not. The name most often attached to the unsettling half of the 3I/Atlas conversation is Avi Loeb. He is a theoretical physicist at Harvard, former chair of the astronomy department, and director of the Galileo project, which studies anomalous objects in our sky with the explicit willingness to consider non-natural explanations. Loeb did not invent the concept of an artificial interstellar object. He did, however, bring it into serious academic discussion when Oumuamua passed through in 2017. With 3I/Atlas, he returned to the idea publicly, not as a claim, as a question. Loeb's argument about the nickel signal goes like this. In industrial chemistry on Earth, there is a specific process for refining metallic nickel. It is called the Mond process. The method works by combining raw nickel with carbon monoxide gas at moderate temperatures to form nickel tetracarbonyl, a volatile liquid. The liquid is then heated further, at which point it breaks down and releases pure nickel metal while freeing the carbon monoxide. Industries use this process to produce high-purity nickel for coatings, alloys, and specialized metal products. The byproduct of the Mond process, when it operates, is a gas plume rich in nickel atoms and carbon monoxide, with very little iron present. Iron is specifically excluded because it does not form carbonyls under the same conditions. The chemical signature of industrial nickel refining, in other words, closely resembles a gas plume of pure nickel without iron. Loeb pointed out this similarity publicly. He did not claim 3I/Atlas was a refinery. He claimed the chemistry is rare in nature and common in industry. And he argued that, when the data is strange, every explanation deserves to be on the table until evidence rules it out. The mainstream response has been firm. Most comet scientists argue that nickel carbonyl can form naturally in cold, icy environments, though direct evidence of this in space remains limited. They point out that nickel-rich emissions have been seen in other comets, including 2I/Borisov and several local ones, without any suggestion of industrial origin. They argue that the extreme ratio on 3I/Atlas is unusual but not incompatible with natural chemistry, especially once iron begins to appear later in the approach, which it did. So the scientific consensus is that 3I/Atlas is a comet. A weird comet, yes. A comet with unusual chemistry, yes. But a comet. Loeb created a personal ranking scale, from 0 to 10, to assess interstellar objects. 0 means natural comet. 10 means alien technology posing a major threat. For 3I/Atlas, he settled on a 4. Unusual enough to warrant attention, not high enough to sound an alarm. In his own writing, he places the object below Oumuamua in anomaly score, partly because Oumuamua never showed visible cometary activity, while 3I/Atlas clearly does. That dynamic, the professional astronomer explaining carefully why the anomaly does not prove anything, and the Harvard professor publicly asking whether we should look more closely, has defined the public conversation about 3I/Atlas for almost a year, and the anomalies, more of them, kept coming. Because nickel without iron was only the opening move. The next strange reading had nothing to do with metals at all. It had to do with the exact direction the object chose to travel through our solar system. A rock tumbling in from interstellar space should arrive on a random trajectory. The galaxy does not aim its wanderers at anything. Over billions of years of gravitational encounters and chaotic scattering, the angle at which an interstellar object enters our solar system should be a coin toss across all possible directions. The math of probability is very specific about this. Our solar system is a flat disk. The planets orbit roughly in one plane, called the ecliptic. If an interstellar object arrives on a random angle, the chance that its path happens to line up closely with that plane, instead of plunging in at some random tilt, is small. 3I/Atlas came in aligned to the ecliptic within roughly 5 degrees. The calculation of how likely that is, given a truly random entry, comes out to about 0.2%, roughly 1 chance in 500. A small enough number that researchers paused and asked whether our statistical framework was complete, or whether this was simply a rare roll of the dice. It gets more specific than that. The Milky Way's thick disk, the old galactic population that 3I/Atlas appears to have come from, is tilted about 60 degrees relative to the plane of our solar system. That means the object's home region is not aligned with our ecliptic at all. A random object from the thick disk should enter our system at roughly that 60-degree angle, not flat along the ecliptic. Something about 3I/Atlas's trajectory put it almost perfectly parallel to our planetary plane. There are 2 categories of explanation. The first is chance. 1 in 500 events happen all the time in astronomy. There is no scientific rule that a rare alignment must mean anything. It could be exactly what it looks like. A lucky coincidence, nothing more. The second category is that the statistics we use to estimate the entry angles of interstellar objects are not fully calibrated yet. We have only observed 3 of these objects in history. 3 is a small sample. If the actual distribution of interstellar arrivals turns out to favour alignment with host systems for reasons we do not yet understand, maybe because of how planetary systems interact gravitationally with passing objects at a galactic scale, then the 1 in 500 number is wrong. The alignment could be natural and common, and we simply do not have enough data to know. There is also the third category, the one the more cautious scientists dismiss, and the more provocative ones entertain. An aligned trajectory is what you would expect from an object that was aimed. If you wanted to move through a solar system quickly and visit its inner planets efficiently, you would follow the ecliptic. That is where the targets are. No one has evidence that 3I/Atlas was aimed. The alignment remains unexplained but has prosaic possibilities. But when unusual chemistry stacks with unusual trajectory, the pattern draws attention. That is how mysteries get built in astronomy. One anomaly is a curiosity. 2 anomalies on the same object are a question, and the object's path had more to say. Because once astronomers look closely at the direction it was travelling within the ecliptic, they notice something else. It was moving against the flow. Everything in our solar system moves one way. Seen from above the Sun's north pole, the planets orbit counterclockwise. Earth, Mars, Jupiter, Saturn, all of them swing the same direction around the star. The asteroids do too. Most comets do too. The rotation is baked into the system, a leftover from the spinning cloud of gas that collapsed to form the Sun and its planets 4.5 billion years ago. Going the wrong way is called retrograde motion. Something orbiting retrograde is moving clockwise when everything else is moving counterclockwise. It is the solar system equivalent of driving against traffic on a highway. 3I/Atlas moved retrograde. The object entered the plane of the planets on a path that ran opposite to the direction every planet travels. While Earth was sweeping around the Sun at 67,000 miles per hour in one direction, 3I/Atlas was plunging through the same plane in the opposite direction at more than 150,000 miles per hour. The relative velocity between the two, when they were closest, was extreme. For an interstellar object, Retrograde motion is not especially strange. An object arriving from outside our system has no obligation to obey our system's rotation. It is tumbling in on a path set by the galaxy, not by the Sun. Roughly half of all interstellar arrivals should, on average, end up retrograde simply because there is no reason to prefer either direction. The strangeness comes when you combine the retrograde path with the alignment to the ecliptic. A randomly arriving object is more likely to come in at some random tilt relative to our planetary plane. A retrograde object aligned closely to the ecliptic is, statistically, an even rarer subcase than a prograde object aligned to the ecliptic. The two constraints, moving against the flow and moving in the same plane, compound each other. Practically, the retrograde motion had consequences. It meant 3I/Atlas crossed the paths of our planets much faster than a prograde visitor would have. It meant any spacecraft trying to observe it had a very narrow window, because the relative velocities were high enough that tracking the object was difficult. It meant that every close encounter with a planet, like the one with Mars in October, was a brief, fast blur rather than a leisurely flyby. And it meant something else, something the more imaginative researchers noted. A retrograde path within the ecliptic plane is the path that maximizes exposure to the planets of the system. Moving the wrong way, you pass every planet in turn as they come around to meet you. You see them all, briefly, in rapid succession. If you were designing a trajectory to survey the inner planets of a solar system in a single pass, retrograde in the ecliptic plane would be an efficient choice. The mainstream view is that none of this requires intent. Rocks can end up on retrograde ecliptic paths through purely natural gravitational histories. A slingshot around the right kind of star, an ejection from a binary system, a brush with a passing gas giant. Any of these can produce a trajectory that, by coincidence, happens to line up with the planetary plane of some other star system billions of years later. But the list of coincidences was growing, and the Very Large Telescope had not finished reporting anomalies yet. Another signal, a molecule associated with life chemistry, was about to appear in the Coma. On August 14th, 2025, the Very Large Telescope in Chile caught another spectral line coming off 3I/Atlas, Cyanide. The emission was clear, repeated and consistent with measurements seen in many other comets. On its own, cyanide in a comet is not alarming. It is actually common. The molecule forms naturally in the cold, irradiated environments of comet surfaces. It is a carbon-nitrogen compound, and it tends to appear alongside other organic molecules in cometary spectra. Every well-studied comet in our solar system has shown cyanide at some level. In fact, the first definitive chemical analysis of a comet ever performed, done in the late 19th century on Halley's Comet, detected cyanide and caused a minor public panic when people realized Earth was going to pass through the tail. The interesting question for 3I/Atlas was not whether it had cyanide. It was how much, and in what proportion to everything else. The measurements showed that cyanide in the Coma of 3I/Atlas was present in roughly normal ratios compared to local comets. The signal was there, strong enough to measure, and it behaved the way cyanide behaves in any comet approaching a star. It varied with distance. It brightened as the object warmed. It faded as the Coma thinned. In a sense, the cyanide was reassuring. Among all the unusual signals coming off 3I/Atlas, this one was ordinary. It suggested that, underneath the anomalies, the object really did contain the same basic organic chemistry that local comets carry. Carbon, nitrogen, hydrogen and their combinations. The same kind of chemistry that, in a different environment and over the right timescales, leads toward the molecules of life. That detail opened a different kind of conversation. Interstellar comets carry chemistry from their home systems across vast distances. Every time one passes through our solar system, there is theoretical possibility that some of the material it sheds could seed local environments with molecules from elsewhere. The dust grains released from the Coma, the organic compounds carried by that dust, could, in principle, drift into the atmospheres of planets or onto the surfaces of moons. Nobody claims 3I/Atlas delivered alien organics to Earth. The geometry was wrong, the distance is too great, the quantities too small. But the broader question is real. Over the history of the galaxy, how much chemistry has been exchanged between star systems by travelling comets like this one? The answer depends on how many interstellar comets exist and how often they pass through populated systems. We used to assume the number was very small. With 3 discoveries in 8 years, the estimates have climbed sharply. Some recent models suggest that at any given moment thousands of interstellar objects may be passing through the inner regions of our solar system, most of them too small or too distant for our current telescopes to catch. Each one of those objects, if it is anything like 3I/Atlas, is carrying its own chemistry, its own organic compounds, its own record of a distant planetary system. The galaxy in this view is a slow-motion exchange program. Comets from different stars drifting through each other's neighborhoods, sharing pieces of themselves. And if that exchange is real, it means the conditions for prebiotic chemistry, the molecules that precede life, may not be isolated to single star systems. They may be travelling constantly, just like 3I/Atlas. And just like the next reading pulled from the object's Coma, which turned the anomaly list even stranger. Look at 3I/Atlas's orbital plane from the side. You would see a thin line, almost laid flat against the larger disk of our solar system. Look at it from above. You would see it arrow across the plane of the planets, straight through the region where every major world we know orbits the Sun. The tilt of an orbit is called its inclination. For 3I/Atlas, the inclination is extremely low relative to the ecliptic, which is what keeps it travelling so closely in the plane of the planets. A steeply tilted orbit would have taken it up above the plane, or down below, missing most of the inner solar system's real estate entirely. A low inclination kept it close to everything. That choice of path, natural or otherwise, determined what we got to observe. Because it stayed near the ecliptic, 3I/Atlas passed relatively close to multiple planets during its brief visit. It dove through the region where Mars orbits. It cut past the inner solar system, where Earth and Venus live. It exited through the outer part of the asteroid belt, heading out toward Jupiter's orbital distance. Every one of those zones had spacecraft or planets in it. Everyone offered a chance for observation. Compare that to the 2 previous interstellar objects. Oumuamua came in on a steep high-inclination path in 2017. It crossed through the inner solar system but did not pass near any planet closely enough for dedicated spacecraft observation. It was gone before we could mobilize a response. 2I/Borisov in 2019 was on a more cooperative path but was much smaller, and its perihelion distance kept it outside our home planet's immediate neighbourhood. Both previous visitors taught us a lot, but neither offered the combination of size, proximity, and low inclination that 3I/Atlas provided. 3I/Atlas gave us the full access pass. Mars watched it first. On October 3rd, 2025, the object passed within about 4/10 of an astronomical unit of Mars. That is roughly 37 million miles, close enough that NASA's Mars orbiters and surface rovers could point their cameras skyward and catch the visitor in their viewfinders. Perseverance, the rover that was roaming Jezero crater at the time, briefly looked up from its geology work to photograph the comet with its mast cam. A robotic machine on one planet took a picture of a rock from another star while both were in motion. Then, less than 4 weeks later, came the closest approach to our own star. October 29th, perihelion. The moment when 3I/Atlas reached its minimum distance from the Sun, about 1 1/3 astronomical units, a distance between the orbits of Earth and Mars. That was also the moment when the object accelerated to its peak velocity, around 153,000 miles per hour, and began the slingshot curve that would aim it back toward deep space. Only one problem. From Earth's point of view, the Sun was directly between us and the comet during those critical days. We could not see it. The glare was too bright. The angle was wrong. A period of blackout began, exactly at the moment of the most dramatic heating, the most intense outgassing, the most revealing chemistry. Every telescope on Earth was blind to it, but not every telescope in the solar system. On May 7th, 2025, when 3I/Atlas was quietly active in the archived test data, the object was more than 6 astronomical units from the Sun, past Jupiter, in the deep cold, in a region of space where, by every known rule of cometary behavior, water ice should have stayed frozen solid. And yet, something was releasing water vapor. The measurement came from NASA's Swift Observatory, which detects ultraviolet light. When water molecules in a comet break apart under sunlight, they release hydroxyl, a molecule made of one hydrogen atom bonded to one oxygen atom. Hydroxyl glows faintly in ultraviolet. Swift detected that glow around 3I/Atlas at a distance where it should have been impossible. The production rate came in at roughly 40 kilograms of water per second, steady, clear, measurable, at a point in space where the sunlight reaching the object was too weak to sublimate pure water ice from a surface. That mismatch forced a rethink. Something else had to be lifting the water off the nucleus. One candidate was buried pockets of carbon dioxide or carbon monoxide ice. Those volatiles sublime at much lower temperatures than water. As the carbon dioxide escaped from cracks in the surface, it could have dragged embedded water ice grains with it, physically carrying them off the nucleus before they had a chance to warm individually. The water would then sublime later, out in the Coma, where the environment was different. Another candidate was amorphous water ice. Not the crystalline kind you find in an ice cube, but a glass-like version formed at extremely low temperatures. Amorphous ice can trap other gases inside its structure like sponge, then release them suddenly when it warms even slightly. The release can trigger cascades of activity at temperatures where normal ice would stay dormant. If 3I/Atlas was rich in amorphous ice, which is expected for an object formed in very cold conditions, its behavior far from the Sun would make physical sense. A third possibility, the one that draws more speculative attention, is that the object has an internal heat source, a chemical reaction deep inside the nucleus, a radioactive decay signature, something that keeps parts of the interior warmer than the external environment should allow. In a 7-billion-year-old rock, exotic chemistries cannot be ruled out entirely, though none of the data specifically requires one. What matters is the observed fact. 3I/Atlas was losing water vapor far from the Sun, at a scale that implies vast reserves of volatile material locked inside it. A rock that carries that much water is, in a real sense, an ice world in miniature. A travelling shard of some ancient cold region of its home system, still releasing its cargo billions of years after being launched. That cargo has meaning beyond chemistry. Water is the universal solvent, the necessary ingredient for every form of life we know. Finding it in abundance on an object that travelled between stars says something about how common water may be across the galaxy. If every interstellar rock carries this much water, the galaxy is not just full of dust and hydrogen, it is full of distributed reservoirs of the most important molecule for life, constantly moving from one system to another. And as 3I/Atlas approached our star, that movement was about to accelerate dramatically, because the sun's gravity was about to give it the hardest shove of its existence. Every object that falls toward a star gets accelerated. The pull of gravity is relentless, and the closer an object gets, the harder the pull becomes. For 3I/Atlas, the approach to the sun was the moment when that relentless pull did its most dramatic work. The object entered our solar system at roughly 36 miles per second, as measured against the sun's rest frame. That was already blistering. It was the speed the object had been carrying through interstellar space, set by whatever ancient event had launched it from its home system. As it approached our star, that speed climbed. By the time 3I/Atlas reached perihelion on October 29th, 2025, its velocity had risen to about 42 miles per second, which works out to approximately 153,000 miles per hour. The increase came entirely from the sun's gravitational pull. The object was falling, and falling fast. Here is the key insight about what that acceleration means. The sun did not give 3I/Atlas any energy. Gravity works both directions. On the way in, the sun accelerates the object. On the way out, the sun decelerates it by the same amount. The kinetic energy gained during the approach is exactly matched by the kinetic energy lost during the departure. It is an accounting balance that the universe strictly enforces. That is why, once 3I/Atlas leaves our solar system, it will return to roughly the same 36 miles per second it carried when it arrived. The sun is not a launching pad. It is a brief curve in a longer journey. The object enters and exits at the same interstellar velocity, with only a change of direction. The direction change is, itself, the most important thing the sun gave the object. Gravitational slingshots do not typically add much speed to an object already moving this fast, but they bend the path. 3I/Atlas entered from the direction of Sagittarius, and will exit toward a different part of the sky entirely, carrying the imprint of its solar encounter into the next chapter of its interstellar journey. For the telescopes watching, the perihelion moment was the most intense observation opportunity of the entire visit. The heat on the nucleus peaked, the outgassing reached its maximum rate, the Coma grew its brightest and widest. Every volatile compound in the object was sublimating at its highest rate, producing the richest spectral signal the instruments would ever capture. And then, frustratingly, the geometry of the encounter hid the comet from Earth. At perihelion, 3I/Atlas was on the far side of the sun from Earth's point of view. The sun itself was directly between us and the object. Every Earth-based telescope and most Earth-orbiting telescopes were blinded by solar glare. For a period of roughly 2 weeks, from mid-October to early November, the most important moments of the comet's visit to our system were effectively invisible from our planet. What astronomers had anticipated and planned for was that the spacecraft scattered across the solar system might catch what Earth could not. NASA and ESA coordinated a response. Missions in transit to other destinations were quietly reoriented. Instruments already watching the sun were retasked. Spacecraft orbiting other planets were pointed at the blackout zone. a fleet of robotic eyes scattered from Mercury's orbit out to Jupiter's, prepared to witness what Earth could not. And at least one of them was about to fly directly through the comet's exhaust. When Earth-based telescopes went blind, the solar system's spacecraft took over. What happened in those weeks around perihelion was one of the most coordinated observation campaigns in the history of comet science. A distributed network of robotic instruments scattered across hundreds of millions of miles of space turned its collective attention on a single object. NASA's MAVEN spacecraft orbiting Mars used its ultraviolet instrument to photograph the hydrogen clouds surrounding the comet. The hydrogen came from water molecules being broken apart by sunlight, the same kind of signal Swift had measured earlier, but now captured in detail from a spacecraft close to the target. MAVEN's images revealed the scale of the hydrogen envelope, stretching farther than the visible Coma. NASA's Perseverance rover, sitting on the surface of Mars, pointed its mast cams skyward during the Mars flyby on October 3rd. The result was one of the most unusual images in the history of planetary science. A rover on one planet taking a photograph of a rock from another star system as that rock passed through the neighborhood of the planet it was exploring. The Psyche spacecraft, in transit to a metal-rich asteroid, turned its camera on the comet and captured 4 observations over an 8-hour window. The Lucy spacecraft, on its way to the Trojan asteroids near Jupiter, also caught the comet from about 240 million miles away. The Stereo mission, a pair of spacecraft that watches the Sun, produced stacked colorized images showing 3I/Atlas as a visible point of light against the solar background during the period when Earth could not see it. The Punch mission, which observes the solar wind and the inner heliosphere, captured images of the comet's tail elongating as the solar wind pushed on it. NASA's SPHEREX observatory, which normally surveys the sky in infrared to map cosmic history, set aside a week of operations to collect data on 3I/Atlas. Infrared observations are particularly powerful for measuring the composition of cometary gases and the temperature of Coma particles. The European Space Agency's JUICE spacecraft, on a long journey to Jupiter's icy moons, took observations of the comet during its inner solar system transit. Due to the thermal constraints of JUICE's trajectory, the data from those observations did not reach Earth until February 2026, months after they were collected. When they arrived, they added detail to the picture. NASA's Europa Clipper, also bound for Jupiter, was predicted to pass potentially through the ion tail of 3I/Atlas between late October and early November 2025. If the prediction held, it would have been the first spacecraft ever to fly directly through the exhaust of an interstellar object. Europa Clipper carried instruments capable of detecting the solar wind changes and magnetic draping signatures that such a transit would produce. ESA's Hera mission, observing asteroid systems, was similarly predicted to graze the ion tail of 3I/Atlas during late October. The geometric encounters would have provided direct sampling of material that originated from another star. Together, the spacecraft fleet produced the most complete picture ever assembled of a single interstellar object. From multiple angles, at multiple wavelengths, from multiple distances, at multiple moments in time, our instruments watched. The combined dataset was larger than anything collected on either of the 2 previous interstellar visitors, and one observation, pulled from that massive pile of data, kept refusing to make sense. The object was accelerating in a direction that gravity alone could not explain. Comets are not perfectly predictable. As a comet approaches a star, the gas jets escaping from its surface push back on the nucleus, like tiny thrusters firing in various directions. The result is a small deviation from the path that pure gravity would predict. Astronomers call this non-gravitational acceleration. For most comets, it is a minor effect, a nudge of a few meters per second over a close approach. 3I/Atlas had non-gravitational acceleration too. That part was expected. What was not expected was the direction. In a typical comet, the jets push the nucleus away from the Sun. The sunlit side of the comet is the side where ice sublimates fastest, because that is where the heat is. As gas blasts off the sunlit surface, the nucleus is pushed in the opposite direction, away from the Sun. This produces a standard, radial, outward-pointing, non-gravitational acceleration. 3I/Atlas's non-gravitational acceleration was not purely radial, it had a substantial sideways component. The object was being pushed off-axis, in a direction that did not align with a simple sunward heating explanation. That detail is unusual but not unprecedented. Other comets have shown off-radial accelerations, usually attributed to a symmetric outgassing from the rotating nucleus. If jets are concentrated on one side of the comet and the nucleus is spinning, the average push over time can end up tilted rather than pointing straight outward. The geometry of the jets and the rotation together determine the net direction. So one natural explanation is that 3I/Atlas has concentrated jets on specific parts of its surface, and that the rotation is combining with the jet geometry to produce the sideways push we measure. That fits with the observations of jet structures in the Coma. But the analysis gets complicated when you try to match the measured acceleration to a specific, plausible jet configuration. Some researchers have argued that the sideways component is larger than a simple, rotational jet model easily explains. Others argue that it fits within the expected range for an unusually asymmetric comet. This is where the conversation about 3I/Atlas split along familiar lines. Mainstream comet scientists treat the non-gravitational acceleration as a fascinating measurement that constrains models of the nuclear structure and jet activity, but that does not require any exotic explanation. More speculative researchers, Avi Loeb prominent among them, noted that the sideways acceleration resembles, in general form, the kind of trajectory adjustments you would expect if the object were under some kind of non-natural control. No one claims the object is thrusting. The measured acceleration is small. But when you stack the anomalies, low inclination, nickel without iron, carbon dioxide dominance, extreme age, early activity, retrograde motion, sideways push, the pattern is what draws attention. Each anomaly on its own has a natural explanation. Taken together, they paint a portrait of an object that seems to break many of the normal rules. One of Oumuamua's main anomalies, in 2017, was its non-gravitational acceleration. That earlier object had no visible coma, no outgassing signature, and yet its path deviated from gravity alone. That was the mystery that first made astronomers wonder whether interstellar objects might occasionally be something other than simple rocks. 3I/Atlas does have a coma. The acceleration is more easily explained. But the echo is there. A second interstellar visitor in a decade drifting just slightly off the path gravity predicts. And as it began to leave the inner solar system, heading back toward the dark, more surprises were still emerging. The object was releasing methane. By April 2026, 3I/Atlas had already passed beyond the orbit of Jupiter, accelerating back outward on its hyperbolic exit. The coma was thinning, the outgassing was slowing. The grand phase of the visit was ending. Most observations were winding down. Many of the major telescopes had moved on to other targets, and the comet was fading. Then a new signal showed up: methane. Methane is a volatile gas, a simple molecule of one carbon atom bonded to 4 hydrogen atoms. On Earth, it is produced both geologically and biologically. In space, it is a common ingredient of icy bodies formed in the cold outer regions of planetary systems. It freezes at very low temperatures and sublimates only in specific conditions. The appearance of methane in the Coma of 3/Atlas, late in its journey, carried a specific implication. It suggested that deeper layers of the nucleus were now being exposed. The outer crust, the reddish surface processed by billions of years of cosmic radiation, had been sublimating and eroding away during the close approach. Below it, fresher layers of the interior were now reaching the surface, where the weakened sunlight of the outer solar system could still warm them just enough to release methane. That matches a model of the comet as a layered object. Not a uniform ball of ice, but something with internal structure. Different volatiles locked at different depths. Carbon dioxide, water, cyanide, nickel-bearing compounds, methane, each in its own zone within the nucleus, each emerging when the right combination of heat and depth was reached. The implication is that 3I/Atlas has not yet shown us everything. There are layers inside it we have not sampled. If the object continues to outgaze as it heads outbound, future telescopes might catch signals from even deeper zones, revealing chemistry that has been locked away for all 7 billion years of its existence. The methane detection also connects to something else. On Earth, methane has a complicated origin story. Much of it comes from biological sources, including microbial life. But in space, methane is purely abiotic, produced by processes that do not involve any form of life. Detecting methane on an interstellar comet does not suggest life on that comet. It does suggest that the chemistry of its home system included the same cold temperature processes that produce methane in our own outer solar system. Titan, Saturn's largest moon, has lakes of liquid methane on its surface. Pluto has methane ice. Comets in our own Oort cloud carry methane. The molecule appears wherever ices were able to form and survive at the right temperatures. 3I/Atlas carrying methane tells us that its home system, wherever and whenever it was, had the same cold chemistry conditions that produce methane-rich bodies in ours. That similarity is itself interesting. The chemistry of distant, ancient star systems may follow the same basic rules as our own. Different ingredients in different proportions, yes, but drawn from the same chemical toolkit. The methane came late, it came quietly, and it came as the object was beginning to fade from view. But before 3I/Atlas disappeared back into the dark, it had one more planet to visit, and the encounter would be close. On March 16th, 2026, 3I/Atlas reached its closest approach to Jupiter. The object came within a few 100 million miles of the gas giant, close enough for the largest planet in our solar system to briefly exert a measurable gravitational influence on its path. Jupiter is massive. Its gravitational reach is enormous. Any object passing close enough gets pulled, at least slightly. For 3I/Atlas, moving at its interstellar velocity, the Jupiter encounter was a minor course correction rather than a capture. The comet was going too fast for Jupiter to hold, but the planet did nudge it, bending its outbound trajectory by a small amount and slightly modifying the direction it would exit the solar system. Jupiter itself had spacecraft nearby. Juno, which had been orbiting Jupiter since 2016, was in the region. The Jupiter Icy Moons explorer JUICE, which was en route to Jupiter's moons, had already taken observations of 3I/Atlas earlier in the year. Europa Clipper, still on its way, was also positioned to observe. The Jupiter flyby was less about Jupiter and more about what we learned from watching the encounter. By measuring exactly how the comet's path was altered by Jupiter's gravity, astronomers could refine their estimates of the comet's mass. Gravity does not care about what an object is made of. It only cares about how much of it there is. A heavier comet gets bent less by a planet's pull. A lighter comet gets bent more. The deflection is a direct probe of mass. The resulting estimates of 3I/Atlas's mass fell in a specific range, consistent with a nucleus several kilometers across, a density typical of other comets, and a total mass in the tens of billions of tons. Some early estimates pushed higher, possibly as much as 33 billion tons, though the uncertainties remain significant. Those numbers carry weight. A rock that massive, moving at that velocity, carries an enormous amount of kinetic energy. If, hypothetically, an object of that size and speed were to hit a planet, the result would be catastrophic on a scale that dwarfs any known impact in human history. The dinosaur-killing asteroid, 66 million years ago, is estimated to have been roughly 6 miles wide, not much larger than 3I/Atlas's upper size estimate. It wiped out 3/4 of all life on Earth. 3I/Atlas, obviously, is not hitting us. Its trajectory never brought it closer than 170 million miles to Earth, far beyond any danger zone. But the mass comparison underlines a sobering point. The galaxy throws objects like this through our neighbourhood regularly, at enormous speeds, and most of them we do not detect until they are already here. For 3I/Atlas, the Jupiter encounter was the final gravitational interaction with our system. After March 16th, the object continued outward, on a path that would take it past the outer planets and eventually out into interstellar space, permanently. The deflection from Jupiter's gravity had set the final direction it would carry for the next several billion years of its journey. Wherever it ends up next, the path was decided in our neighbourhood, and as it moved away, the question that had been quietly building all along came back to the surface. How many more of these are out there? December 19th, 2025. That was the day 3I/Atlas reached its closest point to Earth. Not close enough to threaten anything, but close enough to matter for observation. The minimum distance was 1.8 astronomical units. In plain terms, about 170 million miles. That number deserves context. The Sun is 93 million miles from Earth. The Moon is around 240,000 miles. Mars, when closest, comes within about 40 million miles. Jupiter, at its nearest, is around 390 million miles away. 3I/Atlas, at its closest, was farther than Mars and closer than Jupiter. It passed through a region of space we can study with our best instruments, without ever being remotely close to Earth. The word close has to be used carefully in this context. 170 million miles is close for an interstellar object. It is extraordinarily far for anything that could affect us directly. The gravitational pull of the comet on Earth was too small to measure. Any material shed from the comet, any dust, any gas, dispersed into the vast emptiness long before it could reach our atmosphere. So when a headline says an object is heading toward Earth, it can mean many things. In this case, it meant that 3I/Atlas was going to pass through the inner solar system on a path that brought it nearer to our orbit than most distant comets ever come. That was scientifically exciting. It was not dangerous. but the geometry of the flyby did create a specific observing condition. On December 19th, Earth was on the opposite side of the Sun from 3I/Atlas during the closest approach moment itself. The comet and Earth were both in motion, but the relative geometry meant that the best views from Earth came in the week surrounding the closest approach, rather than on the exact day. Ground-based telescopes tracked it across the sky through November and December, building a continuous record of its behaviour. By the time of closest approach, 3I/Atlas had already passed perihelion and was heading back out. The Coma was still active but was beginning to thin. The object was still bright enough to observe with amateur telescopes under dark skies, though it never became a naked-eye comet. Most people on Earth would never have known it was there if the news had not reported it. That is one of the quiet truths of cosmic visitors. We are surrounded by objects that pass through our neighbourhood, some close, some far, most invisible to the unaided eye. Every day, tons of interplanetary dust drift onto Earth from the debris of ancient comets. Every month, small rocks from the asteroid belt cross our orbit. The sky is busier than it looks. 3I/Atlas was just the biggest and most unusual visitor of recent memory. Its passage was a reminder that our solar system is not an isolated bubble. It is an open neighbourhood, with regular traffic passing through, some of it coming from other stars entirely. And here is the part that should shift your perspective. Of the 3 interstellar objects we've ever detected, 2 of them passed within the orbit of Mars. The galaxy sends its wanderers straight through our most populated zone more often than old models predicted. Which raises a harder question. How many have we missed? For most of human history, interstellar objects went undetected. Our telescopes were not sensitive enough. Our surveys did not cover enough sky. Our software was not smart enough to flag rapid moving objects against the background of stars. Every interstellar visitor that passed through the solar system before 2017 did so in complete anonymity. Then Oumuamua, then Borisov, then 3I/Atlas. 3 confirmed objects in 8 years. The frequency of detection has climbed sharply, and that climb is telling us something about what has been happening all along. The math is straightforward. We did not suddenly get a burst of interstellar visitors in the late 2010s. Interstellar objects have been passing through our solar system for the entire 4.5 billion years of its existence, at rates that have probably remained roughly constant. What changed in 2017 was our ability to see them. Before Oumuamua, surveys were catching maybe 10 to 20% of the objects they should have been finding. Since then, with new telescopes coming online and better software tracking fast-moving objects, detection rates have improved, but we're still catching only a fraction of what passes through. Current estimates, built from the detection rates of the 3 confirmed interstellar objects, suggest that thousands of interstellar rocks may be inside Earth's orbital distance at any given moment. Most of them are small, the size of a car or smaller, far below the detection threshold of current telescopes. Some of them are larger, comparable to Borisov or Oumuamua, and these we might catch if we're lucky. Rocks the size of 3I/Atlas, multi-kilometre nuclei, are rare. They probably pass through our solar system every few years, possibly every decade, at rates that we've only begun to estimate. We caught this one because we had the right telescopes pointed at the right patch of sky at the right time. That is the scary part if you choose to see it that way. We have been catching interstellar visitors in our cosmic backyard for only 8 years. For the 4.5 billion years before that, they came and went without being noticed. Some of them may have passed close, some of them may have been bigger than 3I/Atlas. We have no way to know. Some scientists have begun asking whether a past interstellar impact might explain specific anomalies in our solar system's history. Strange orbital features, unusual craters, missing time in geologic records. These are fringe ideas, but they are becoming more discussed as the statistics of interstellar traffic are refined. The main point is this: the galaxy is busier than our models used to suggest. Objects from other stars are moving through our neighbourhood constantly. Most are too small or too far to matter. But the distribution of sizes is a real distribution, and the big ones exist, and they do occasionally come close. 3I/Atlas did not hit us. It did not come close enough to be a threat. But it passed through, measured, observed, studied, and every one of its measurements helps calibrate our estimates of how often bigger ones come close. The next detection will come. That much is certain. The only questions are when and what it will look like, and one upcoming telescope is about to change the answer dramatically. High in the Chilean Andes, on a mountaintop called Cerro Pachon, a telescope has been coming online over the past few years, the Vera C. Rubin Observatory. It is a survey instrument designed to photograph the entire southern sky every 3 nights, catalogue every object in view, and track every moving point of light across the solar system. Rubin is not like other telescopes. It does not zoom in on specific targets. It sweeps the sky systematically, relentlessly, collecting data on a scale that older instruments cannot match. The camera at its focus is the largest digital camera ever built, with a sensor capable of capturing images containing more than 3 billion pixels. Each exposure covers an area of sky 40 times the size of the full moon. Over the course of its 10-year main survey, Rubin will image the sky more than 800 times. The result will be a continuously updated movie of the universe, showing every object that moves, every star that brightens, every supernova that explodes, every asteroid that crosses the field. For solar system science, Rubin is transformative. Early commissioning data, collected as the telescope was being tested, already detected thousands of new asteroids in its first brief observation periods. When the full survey is underway, detection rates are expected to climb by orders of magnitude. For interstellar objects specifically, Rubin is the first instrument capable of changing the statistics dramatically. Current estimates suggest that Rubin will detect roughly 1 interstellar object per year during its main survey. That is a huge increase over the historical rate of 1 every few years. Over the course of a decade, Rubin could catalogue 10 or more interstellar visitors, enough to start building real statistics about their properties. Each detection will come with a full set of measurements: trajectory, size, rotation, colour, activity level. Follow-up observations with other telescopes will fill in the chemistry. Over time, we will start to see patterns. Are most interstellar objects small? Are the big ones exceptionally rare? Do they tend to come from specific regions of the galaxy? Do their chemistries cluster into groups, or do they vary widely from one to the next? 3I/Atlas, with all its anomalies, is currently a sample size of 1. We cannot say whether its unusual features are typical for interstellar objects in general, or whether it is specifically strange. Rubin will give us the statistical basis to answer that question. If the next 10 interstellar objects also show high carbon dioxide ratios, nickel without iron, retrograde ecliptic orbits, then we will know these features are common. If none of them do, 3I/Atlas will stand out as genuinely unusual. The telescope is also good for something else. Early warning. If an interstellar object ever does arrive on a path that brings it close to Earth, Rubin will catch it earlier than any other instrument. That extra warning time would matter for planetary defense. We would not be able to stop a multi-kilometer rock moving at interstellar speeds. But we could prepare. We could observe it more completely. We could deploy the full fleet of telescopes with more lead time than we had for 3I/Atlas. Rubin is not finished with its commissioning yet. The full survey ramps up over the coming years. But the revolution has already started. The galaxy, for the first time in human history, is going to be watched continuously. And the watching has already begun to reveal just how full it is. The image of the galaxy that emerges from the 3 confirmed interstellar objects is not the image our models use to project. The old picture treated each star system as a relatively isolated island, with its own planets, its own comets, its own debris, rarely exchanging material with its neighbours. Interstellar objects were thought to be rare enough that even finding one was a lifetime achievement. The new picture, calibrated by recent detections, treats the galaxy as something closer to a circulating ocean of debris. Every planetary system that forms ejects some of its material. Those ejected objects travel over billions of years in long interstellar wanderings. Some of them pass through other star systems. Some of those passes are close enough to be observed. The exchange is not fast, it is not dramatic, but it is constant. The numbers are starting to come into focus. Recent papers estimate that, at any moment, there could be tens of thousands of interstellar objects larger than about 30 feet across inside the orbit of Neptune. Most are too far from the Sun to be detected. Most pass through without being noticed. A few, by chance, come close enough to the inner solar system for our current telescopes to catch. Scale that up. The galaxy contains hundreds of billions of stars. Many, perhaps most of them, have planetary systems. Each one, at some point in its history, has ejected material. Over the lifetime of the galaxy, roughly 13 billion years, the total amount of interstellar debris flung between stars is staggering. Some estimates put the total mass of interstellar objects in the galaxy at values comparable to the mass of the stars themselves. That is a lot of chemistry in motion. If every interstellar object carries, like 3I/Atlas, its own record of its home system's ices and organics, then the galaxy is a giant chemistry experiment, with samples constantly moving from one region to another. The implications for how we think about the origins of life are not small. On Earth, the big questions about how life started have long focused on local chemistry. What molecules formed in our early oceans? What energy sources drove the first reactions? What prebiotic compounds accumulated in specific environments? Those questions remain valid, but the interstellar picture adds a new layer. The molecules that fell onto the early Earth via comets and dust came not just from our own solar system. Some of them, potentially, came from interstellar objects that passed through and deposited material. Over 4.5 billion years, Earth has swept up an unknown but possibly significant amount of material from interstellar sources. Every planet has. The building blocks of every world in the galaxy are, to some extent, shared. The chemistry is not isolated. It is circulating. That changes the search for life elsewhere. If distant star systems share chemistry through this slow circulation, then the molecular precursors for life may be much more uniformly distributed across the galaxy than we used to think. The conditions that produced life on Earth may not have been purely local conditions. They may have included contributions from thousands of interstellar comets that, like 3I/Atlas, passed through, shed their material, and moved on. We have been part of an exchange the whole time. We just did not know, and 3I/Atlas, as it faded from view, was both a messenger and a reminder of what has been passing through all along, of what will pass through tomorrow. Place the three confirmed interstellar objects side by side and they look like different animals. Oumuamua in 2017 was small, elongated, dry. No visible coma, no tail, no outgassing, just a dark sliver tumbling through the solar system with an unexplained acceleration. 2I/Borisov in 2019 was a textbook comet. It had a clear coma, a tail, and chemistry that, apart from being slightly redder and slightly richer in carbon monoxide, looked roughly like a comet native to our system. 3I/Atlas is something else again. It is larger than either of its predecessors, possibly by a large margin. Its nucleus estimates reach up to 3.5 miles, while Oumuamua was perhaps a few hundred feet and Borisov was less than a mile. Its mass, if the upper estimates hold, dwarfs both previous visitors combined. It is moving faster than either, at a velocity that places it firmly in the upper range of expected interstellar speeds. Its chemistry is different. The carbon dioxide dominance is extreme. The nickel without iron ratio is unprecedented. The cyanide production is normal, but most of the other chemical signals diverge from what Borisov showed. Its trajectory is different. The low inclination, the retrograde motion, the close alignment to the ecliptic. Oumuamua came in on a steeper path. Borisov came in on a higher inclination. 3I/Atlas chose, accidentally or otherwise, the geometry that maximized our ability to observe it. Its age is different. Oumuamua's age was never firmly established. Borisov was thought to be a relatively young object, possibly only a few 100 million years old. 3I/Atlas is estimated at 7 billion years or more, making it the oldest interstellar object by a wide margin. What does all that variation mean? It means that interstellar objects are not a uniform population. They do not come from a single type of source. They're not all similar in size, shape, age, or chemistry. Each one is a sample from a different part of the galaxy with its own history. The diversity we're seeing in just 3 confirmed objects suggests that the full population of interstellar visitors is enormously varied. Some come from young planetary systems recently ejected. Some come from ancient systems, long since dissipated. Some are primarily icy. Some are primarily rocky. Some retain their volatiles. Some have been stripped of them by cosmic radiation and time. The population is a mix of all these things, in proportions we are only beginning to estimate. 3I/Atlas, in this view, is not the definitive example of what an interstellar object is. It is one data point. A particularly large, particularly ancient, particularly chemically strange data point. Future detections will add more points. Some may look similar, some may look completely different. The full picture will only emerge as the sample size grows. That is one of the reasons Rubin matters. With 10 or more detections per decade, we can start to understand the distribution. With a handful, we are stuck drawing conclusions from outliers. But even with only 3 examples, one pattern is becoming clear. Each interstellar object we've studied carefully has revealed something unexpected. Something that did not fit the models. Something that forced astronomers to rethink what they thought they knew. That pattern itself may be the most important finding. The galaxy is stranger than our models suggest. When 3I/Atlas passed Jupiter in March 2026 and began its final outbound journey, the scientific community was left holding a list of open questions. Many were specific to the object itself. Others were about what its passage implied for broader science. The specific questions included these. What caused the extreme carbon dioxide ratio? Was it a feature of the home system's chemistry, or a result of long interstellar aging? Why was the nickel-to-iron ratio so unusual in the early observations, and what exactly produced the nickel without iron? Was it cold carbonyl chemistry or something else? What drove the non-gravitational acceleration's sideways component, and was the explanation really just asymmetric jets, or was something more complex at work? Some of these questions may be answered as researchers continue to analyse the enormous data set collected during the object's visit. Spacecraft data, especially from JUICE and the Europa Clipper observations during the Ion-Tail encounter, are still being processed. Papers will continue to appear for years. Each analysis may sharpen or revise the conclusions. Others' questions may never be fully answered. 3 I/Atlas is gone. It is accelerating back out into interstellar space, and there will never be another opportunity to observe it. Whatever data we captured is the only data we'll ever have. If the critical measurement that would answer a specific question was not made during the visit, it cannot be made now. The broader questions are harder still. What fraction of interstellar objects are this unusual? Is 3 I/Atlas typical for interstellar visitors, or is it an outlier that we happen to detect? What does the galactic population of interstellar wanderers actually look like? How much material is really circulating between star systems, and over what timescales? These questions require more data, more detections, more samples. The Rubin Observatory is the primary source of that data for the next decade. Proposed future missions, including dedicated interstellar object chasers that could launch from Earth to intercept a passing object, may provide even more. ESA has already proposed such a mission, called Comet Interceptor, which will wait in space for a suitable target to be detected and then fly to meet it. If Comet Interceptor launches and succeeds, it will provide the first close-up images of an interstellar object, something we did not have with Oumuamua, Borisov, or 3 I/Atlas. Detailed resolution, surface structure, direct sampling of the coma, maybe even direct sampling of the nucleus itself. The broader question, the one that sits quietly under all the others, is what we are missing. What has been passing through our neighbourhood for billions of years, unnoticed, unrecorded, beyond our reach? What stories are written in the ices of those wanderers that we have never read? What history of the galaxy is out there, drifting, crossing our path, moving on? 3 detections have given us 3 data points. Each one has been a revelation. 3 I/Atlas, in particular, has broken more rules than it has confirmed. Its carbon dioxide dominance, its nickel chemistry, its retrograde ecliptic alignment, its extreme age, its active coma at distance, its sideways acceleration. Every measurement challenged some piece of the expected picture, and the object did not wait for us to catch up. It kept moving, it kept fading, it kept carrying its answers deeper into the dark. The final stretch of its visit was a slow disappearance. By April 2026, 3 I/Atlas was a different object than the one that had been discovered 9 months earlier. It was dimmer. Its coma had shrunk, its tail had thinned. The great heat of perihelion was behind it, and as it moved outward, the sunlight reaching it grew weaker by the day. Comets fade. That is what they do when they leave the inner solar system. The volatile ices that had been sublimating furiously near the sun now had less energy to drive them. Outgassing slowed. The coma contracted. dust that had been lifted off the nucleus settled back down or dispersed into the tail's trailing trail of debris. In the final weeks of active observation, some of the largest telescopes on Earth and in space continued to track the object. The Rubin Observatory, the Webb Telescope, the Hubble Telescope, and dozens of ground-based instruments kept collecting data as long as the object was bright enough to analyze. New anomalies continued to appear, like the methane detection and evidence of deeper layers emerging. But the signal was weakening. At some point, the object would fade below the detection threshold of even the most powerful telescopes. It would still exist. It would still be moving at tens of miles per second. It would still be carrying its cargo of ancient ices back into the dark. But we would no longer be able to see it. That moment, when the last telescope loses track of 3I/Atlas, will be a specific date in the near future. After that date, the object becomes invisible to us, and whatever it does next happens in silence. It will keep accelerating outward for a while, pulled forward by the remaining outbound momentum that the sun's gravity cannot reverse. Eventually it will reach a distance where the sun becomes just another star among many, no more influential than any other point of light in its sky. From the object's point of view, our entire solar system will shrink to a single pinpoint in the rearview mirror. And then, interstellar space. True interstellar space. The deep dark between the stars, the same environment the object travelled through for the previous 7 billion years, waiting again. Where it goes from there depends on the geometry of its exit trajectory, modified by the Jupiter encounter. The best models suggest it will continue through our local galactic neighbourhood for a very long time, possibly passing through other star systems over billions more years. Each of those encounters could alter its path further. Over enough time, its trajectory becomes chaotic, impossible to predict. One thing is certain: if another civilization somewhere, someday, observes an ancient rock passing through their solar system with unusual chemistry and a carbon dioxide-dominated coma, there is a chance, a real chance, that the object they see is 3I/Atlas, the same rock we studied, the same rock that drifted past our planet in the last months of 2025, continuing on its endless journey, carrying the same cargo of ancient ices, the same reddish crust, the same nickel-rich exhaust. We were just one stop on a very long journey, and our role, in its story, was brief. Step back from the specific measurements, the anomalies, the spacecraft data, and ask the broader question: what did the visit of 3I/Atlas actually teach us? The first thing is that interstellar objects are more common, more varied, and more chemically interesting than our old models predicted. The diversity of just 3 confirmed visitors, from the dry and tumbling Oumuamua to the textbook comet Borisov to the massive, ancient, anomaly-rich 3I/Atlas, has already reshaped the field. Interstellar objects are not a single category. They are a family of objects with widely varying properties. The second thing is that our solar system is permeable. It has been absorbing and shedding material from other star systems for its entire existence. The idea of a closed, isolated neighbourhood has been replaced by the image of an open ecosystem, connected to the rest of the galaxy by a slow but constant exchange of wandering rocks. The third thing is that the building blocks of chemistry, including the precursors of organics and the ingredients that matter for life, are more widely distributed than previously thought. 3I/Atlas carried water, carbon dioxide, cyanide, methane, and organic compounds, all assembled around another star billions of years ago, and still intact after billions of years in interstellar travel. If its cargo is representative, every corner of the galaxy has access to similar chemistry. The fourth thing is that our detection capabilities are finally approaching the level needed to study this population seriously. The Rubin Observatory, now coming into full operation, will increase the detection rate of interstellar objects by orders of magnitude. Over the next decade, we will move from having 3 confirmed examples to having dozens, possibly hundreds. The statistics will improve, the patterns will clarify, the outliers will become contextualized. The fifth thing is more unsettling. The anomalies on 3I/Atlas taken together suggest that even our best current models of comets do not capture everything that interstellar objects can do. Unusual chemistry, unusual trajectories, unusual activity patterns, each one can be explained individually. But the stacking of anomalies on a single object has driven some researchers to ask questions that most would have dismissed a decade ago. What if some interstellar objects are something other than natural? The mainstream answer to that question is still no. 3I/Atlas is a comet. Its behaviour, however unusual, is within the range of what natural comets can do. The anomalies are surprising but not inexplicable. The nickel chemistry has a natural explanation in cold carbonyls. The trajectory alignment is improbable, but not impossible. The age is old but consistent with galactic timescales. The minority view, represented most prominently by Avi Loeb, is that we should keep the possibility open. Not because there is specific evidence of artificiality, but because the history of science has repeatedly shown that anomalies sometimes do point to things we did not expect. Treating unusual objects as only ever natural, Loeb argues, is a methodological choice, not a scientific conclusion. The conversation between these two views is likely to continue for years, through many more detections. Each new interstellar object will be studied with the question in mind. Each one will add to the statistics. Over time, either the anomalies will fade into the background of normal variation, or patterns will emerge that suggest something more. For now, 3I/Atlas remains what it always was: an ancient visitor, a chemistry lesson, a pointed reminder that we live in a galaxy full of things we do not yet understand. For most of the 20th century, astronomy viewed our solar system as an isolated unit. The Sun, its planets, its moons, its asteroids, its comets, all bound together by gravity and largely sealed off from the rest of the galaxy. Occasional cometary visitors drifted in from the outer Oort cloud, but even those were considered part of our system, just extremely distant parts of it. True outsiders, objects from other stars, were considered theoretical curiosities. That view did not survive the past 8 years. 3 interstellar objects, each confirmed beyond doubt, have punctured the old image. They are not theoretical anymore. They are a measured, documented, studied population. The rate of arrivals suggests that small interstellar objects are common enough to be passing through our neighbourhood continuously. The large ones, like 3I/Atlas, are rarer but not extraordinary. Our solar system sits inside a galaxy that is, by any reasonable measure, enormous, ancient, and densely populated with planetary systems. The current estimate suggests that most of the hundreds of billions of stars in the Milky Way host planets. Many of those planetary systems have gone through violent formation phases, ejecting enormous amounts of debris into interstellar space. Over the 13 billion years the galaxy has existed, the cumulative volume of ejected material is staggering. We are swimming in it, constantly, whether we see it or not. 3I/Atlas, in that context, is not an exception. It is an example. Its passage through our neighborhood is the kind of event that has been happening at some frequency for the entire history of our solar system. The only thing new is our ability to notice. That realization shifts some long-standing questions. When we ask where Earth's water came from, some of it may have been delivered by interstellar objects over billions of years. When we ask where our organic molecules came from, some may have arrived from elsewhere. When we ask how unique the chemistry of our solar system is, the honest answer may be less unique than we assumed, because the ingredients are shared across a vast galactic network of slow exchange. It also shifts how we think about other planetary systems. If they are receiving material from our system and from each other, then the chemical environments of distant worlds are not purely the products of local conditions. They are in part the products of everything they have swept up from the galaxy's flow of debris. That possibility turns the search for life elsewhere into a different kind of search, not for isolated cradles where chemistry happens to produce life independently, but for environments where life-favouring chemistry, some of it delivered from elsewhere, accumulates in conditions suitable for complex development. 3. I/Atlas will pass through other star systems. Its cargo will eventually be released as sunlight from other stars warms it, as it sheds more and more material over billions of years. Some of that material may someday fall onto other worlds. Some of it may participate in very small ways in the chemistry of other planets. The galaxy, in other words, is collaborative at a timescale we're only beginning to comprehend. And the visit of 3I/Atlas was a direct, observable example of that collaboration in progress. One rock, one visit, one glimpse of how much has been moving between the stars all along. 3I/Atlas is gone from easy view. It continues outward, fading, shrinking in brightness, eventually vanishing even from the largest telescopes. In a year or two, even the most sensitive instruments on Earth will lose the signal entirely. The object will continue on its trajectory, carrying its ancient cargo, travelling at the same interstellar speed it brought with it, heading for destinations that cannot be predicted over the billions of years ahead. But here is the final point, the one that matters most after everything else. It is not the last. Another interstellar object is already out there, moving through the dark between the stars heading in our general direction. Maybe several, maybe dozens, maybe thousands of small ones that will never be detected, and a few large ones that will. The galaxy does not stop sending visitors just because we have studied 3 of them. The supply is continuous. The traffic does not pause. The next one could be announced next month, or next year, or in 10 years. The timing depends on chance, on which patch of sky a telescope happens to be watching, on whether the new arrival enters our system at an angle that makes it detectable. The Rubin Observatory will increase the odds dramatically. New surveys already coming online will increase them further. The next interstellar object may be small, like Oumuamua, and pass without much fanfare. It may be a textbook comet, like Borisov, confirming what we already know about cometary behaviour. Or it may be massive and strange, like 3I/Atlas, full of anomalies that rewrite more models. The odds strongly favour safety. The probability that any specific interstellar object will pose an actual threat to Earth, through impact or close approach, is extremely small. Space is vast, Earth is tiny. Most visitors will pass at distances that never register as dangerous. That is the comforting reality of celestial mechanics. But the probability is not zero. Somewhere in the far future, some interstellar object on some specific trajectory will, by chance, come close enough to matter. When that happens, the observational infrastructure we build now, the telescopes, the tracking systems, The planetary defense protocols will determine how much warning we have. 3I/Atlas was a practice run for that scenario, even though it did not come close to threatening us. The coordination of spacecraft, the mobilization of telescopes, the rapid analysis of chemistry, all of that was a rehearsal. The rehearsal went well. The next one will go better. By the time an interstellar object ever does require a serious response, we will have decades of experience studying the ones that passed harmlessly. And here is the thought that might stay with you. Right now, as you finish listening to this, another interstellar visitor is crossing the dark somewhere out there, moving at tens of miles per second, billions of years old, carrying the chemistry of a star system that may no longer exist, approaching a solar system, ours or someone else's, on a path that will reveal it in its own time. It has been happening for billions of years. It will happen for billions more. Most of it will always be invisible to us. But the fraction we do see, the fraction we have finally learned to catch, is teaching us something important. We're not alone in this galaxy in the way we once thought. Our neighbourhood is an open one, and the visitors, when they come, carry more than just rock and ice. They carry the history of places we will never reach, told in a language we're only beginning to learn to read. 3I/Atlas was one chapter of that story. The next one is already on its way.